All right. Next chapter. Okay, so up to this point, we have been talking about elements and atoms and all of that fun stuff. We are now going to go to the next level and talk about compounds, which is the next largest type of particle. Okay, and so we're going to talk about what a compound is, and then we need to be able to name them, because it's kind of hard to talk about them and learn about them if we don't know what they're called. So basically this whole chapter is how to name compounds, because it's a system that we have to learn. Okay, so a compound is pretty simple to understand. It's just a particle made up of multiple elements. Okay, and those elements are held together by a chemical bond. What is a chemical bond? I'm glad you asked. Okay, it's actually kind of hard to define in a very specific way because there's actually lots of different types of chemical bonds. Covalent is one of them. So a good kind of introductory definition is just some sort of attraction that keeps the atoms together. Okay, and they will stay together until something with enough energy can rip them apart. We are going to focus on two types of chemical bonds, which then means we are going to focus on two types of compounds for this chapter. There's a zillion types of compounds we could look into, but for Gen Chem, the two we're going to talk about today are the ones we want to focus on. Okay, I just said that. I'm waiting. It's like orange marker smudged on there. Okay. Two types of compounds. Okay, the first one, covalent compound or a covalent bond. Okay, this is defined as a bond where atoms are sharing valence electrons. Okay, so what we're going to talk about is that atoms will attract electrons toward themselves, and if you have two atoms that have a similar level of attraction, they will then just share the valence electrons between them. Okay, is how we're going to think about it. Okay, and so it makes sense where that word comes from, covalent. They are kind of cooperating in the valence electrons are being valence for two atoms, is how we're going to think about it. Okay, so that's where they are shared, as opposed to if you have two atoms where one of them has a very strong attraction for electrons, it'll just steal the electrons away and we get an ionic bond. Okay. Steal away is the mean way of saying it. The nice way of saying it is electrons are transferred. Okay, but the reality is one of the atoms is very strongly attracting them and it just rips them away. So, however you want to think about it.
So like, that's not really like a bond though.
It is.
It's just like stealing it.
I didn't tell you the next part. I'm going to explain it later. Okay, but good observation. Good observation. I'm coming back around to it. Everywhere. Okay. So here's the deal. Okay. The first thing I want to get into is why these two different types of bonds exist in the first place. I don't know how many teachers go into this when they teach chemistry. Goodness. Sorry, someone's singing. I don't know how many go into this, but I want us to understand why there's these two types of bonds, because it'll make we'll have a better understanding of chemistry instead of being just like, oh, it's just because is not a great explanation. Okay, so in order to understand that, we need to talk about a little thing I like to call electronegativity. Okay, this is how strongly electrons are attracted to a certain atom.
By the way.
Yes.
Do we need to know about this, or is this like a side?
You need to know about electronegativity. Yes, this is not just background information. It's something I want you to know on its own. Okay, so some elements will attract electrons very strongly. Okay, it has to do with the number of protons and how many energy levels are in the cloud, all these different factors. And then other atoms don't attract electrons as strongly when they're in a chemical bond. Okay, and so this spectrum of electronegativity is going to determine what type of chemical bond we're dealing with. Okay, and we're going to use a system that was developed back in the 30s, and this is what chemists still use today. Okay, so there we go. So here's our system. Okay, here's a periodic table with all of the electronegativities for all of the elements that have them, or for the elements that have been measured. Okay, can you find the element with the highest electronegativity? There's one higher than krypton. Fluorine is 3.98. Fluorine is the most electronegative element on the periodic table. Do you guys see the one that's the least electronegative?
Cesium?
Cesium is pretty low. And then cesium or francium, depending on the situation. Yeah. So down here in this corner. Okay, so 0.79 is what this says over here.
What does that mean?
Greater than? I'm not sure. There's a footnote that goes with it, so I'd have to look into it. Yeah. I'm just going to call it 0.79. Okay, so roughly 0.8. Okay, up to 4.0. Okay, and so that's basically the scale that we're working on. Okay, from 0.7 to 4. Okay, and 0.7 means that this atom does not attract electrons very strongly. It can be easily taken. Whereas 4 means that atom is going to pull electrons toward itself very strongly compared to other elements. Okay, and so in general we can see some patterns. Okay, we can see generally as we go down the group, the attraction is not as strong. And if you go across a period, it gets stronger. Okay. I'm pretty sure this is directly related to the size of the atoms, right? If I'm going down a group, what am I adding to my electron cloud each time I go down an energy level? As I add energy levels, those electrons are farther away from the nucleus, aren't they? So they are not as strongly attracted. It's kind of like gravity. We're stuck on Earth because we're close, but if you get far away from Earth, you're not as strongly attracted to Earth. Same idea with electrostatics, the electromagnetic force. If the electrons are farther away, they're not attracted as much. As I go across, now my atoms are getting smaller, and so the electrons can get closer and they can be drawn in more tightly. Okay, and so we generally have very high electronegativity here and very low electronegativity here. Okay, it kind of works corner to corner. Okay, how come there's some elements that don't even have one? Do those noble gases even form chemical bonds? No. Helium doesn't bond to anything neon or argon. You can kind of force krypton and xenon to bond in some circumstances, but these elements here, again, they're super stable. Subshells are filled. There's no energetic reason, there's no energy reason that they would form bonds. Okay, they don't become more stable, whereas these other elements become more stable by forming the bonds. Yeah?
Is there a reason, like there's the exceptions, like...
For these noble gases?
Or more towards the middle.
Oh, like these darker ones?
Yeah.
I'm not sure why there's a little spot there with higher electronegativity. When you're in the D subshell, what the electrons are doing is a lot more complex, and I don't remember learning that off the top of my head. So, sorry, I don't have a good answer for that. But obviously, the general trend is low to high there. Yeah, but there's kind of an interesting little spot there. I'd have to look into that.
Maybe it's oh wait, no, never mind. I was about to say the anomalous thing, but...
Oh yeah, maybe, but yeah, I don't know if it correlates with that, but good thought. Yeah, so anyway, so this is our general trend, okay? And so the reason we care about electronegativity is because this is going to determine what type of chemical bond is formed, okay? So if we go back to our two types of bonds, it's going to depend on the relative electronegativities or the difference in electronegativities. If I have electronegativities that are similar between two elements or two atoms, they're going to share electrons and we will form a covalent bond. Okay, if the electrons are relatively evenly attracted to either atom, they're not going to get ripped from one to the other, they're going to be covalent on two atoms or more, so that we get a covalent bond. If I have electronegativities that are very different, okay, one is really high, one is really low, the electrons are going to be strongly attracted to one of those atoms. So they just get ripped away from one atom and become a part of the other one. And that's where we get an ionic bond. Okay, and so our cutoff here, it's technically a spectrum from very low to very high difference in electronegativity, but a convenient cutoff point is 1.7. So if our two electronegativities are within 1.7 of each other, we're going to say that that's similar enough to make a covalent bond. If I have two elements and their electronegativity is more different than 1.7, the difference is greater than 1.7, we'll say that it's an ionic bond. Okay. Technically it's a spectrum, but it's a common cutoff point, so it just makes things simpler for us. Cool? Okay. So, oops, sorry. Going back. I can just talk about the next slide. Okay. Do you think I'm going to have you memorize the electronegativities for all the elements? Probably not. Probably not. If you want to look it up, which you will need to do, and I'll give you a chart on the test. I have periodic tables, oops, with the numbers on it. That's what this periodic table is. The electronegativities are on there. I've also posted this on Google Classroom, so you can use Google Classroom if you want to look them up. Or if you go to P-Table and click on the Properties tab, it's one of the properties that you can click on, and it'll just pop up on there as well. Okay, so ptable.com is great. There's a link there if you want that, or I've already posted one on Google Classroom, or you can take one of these, or if you already have one, just use that. Okay, or you can just Google it, electronegativity of this. Okay, so you will need to be able to look it up, and of course I'll provide it to you on the test. Okay, so let's say, dang it. Let's say I have some elements and I want to know what type of bonds they'll form. What type of bond would carbon and chlorine form if they bonded together?
Ionic.
Covalent.
How do we figure it out? Some of you saw the answer, I accidentally clicked it, but how would you know that that's the answer?
Because one has more electrons than the other does not.
I don't care about how many electrons, I care about electronegativity. So we need to look it up. If you want to get out your phone, or I don't know if you want to come grab one of these. Okay. What's the electronegativity of carbon? Just take one. I've got two. There you go. They're taken. Okay. What's the electronegativity of carbon? Someone help me out. You can Google it. 2.55?
Would not help. There. Oh wait. Oh yeah, you're right. Let's go down because it has all the electrons.
What about chlorine?
3.16.
3.16? Okay, now what do I do with that?
3.16 minus 2.55.
Find the difference.
Less than 1.7, that's what's called covalent.
Yeah. So I don't know exactly what it is, but it's less than 1.7. It's like 0.91?
0.61.
61. Close enough, yeah. So the difference is similar, that's close enough or small enough in difference that the electrons are not strongly attracted to one side, per se. So that's going to form a covalent bond. We could say that the atoms are sharing the electrons, the valence electrons. What about sodium and fluorine?
0.93. And fluorine 3.98.
3.98 actually.
Greater than 1.7.
Probably greater than 1.7?
Yeah, that's ionic.
Fun fact, sodium fluoride is the active ingredient in toothpaste. This is the chemical that will clean your teeth. Or at least that's what the FDA says. I listened to a podcast about how it's kind of hokey, but I don't know. I can send you that podcast later.
What's the difference between fluoride and fluorine?
Great question. Fluoride is negatively charged. Fluorine is neutral. Yeah, that's coming up next week.
So all the names are neutral on the table.
Right.
And they change.
Right. Right. Titanium and oxygen?
Titanium 1.54, oxygen 3.44. I feel basic math, so
There's like this. Oh wait, or it's the
1.9 is greater, so I don't have.
Yeah, it's more.
So this minus this is 1.9. So they're different enough that the oxygen is going to attract electrons away from titanium, and we make an ionic bond.
Surprisingly easy.
Yeah, it's simple. Everything today should be really simple.
I can use calculator on Excel, right? Because I feel basic math.
Yes.
Thank God. Did you actually fail?
Yes.
You just eyeball it.
I mean, lots of
I mean,
problems
yeah,
with
you're just looking for 1.7,
the
so
basic
yeah.
math are hard. Like 60.
I don't think there's a single question where I actually want you to calculate it. I just want you to tell me what type of bond it is. So if you can eyeball it, that's fine.
What if you eyeball it wrong?
Then you get it wrong. Okay, make sense? Okay,
Yes.
great. So, a little bit about covalent compounds, okay? So, I already said electronegativity is going to be similar. Now, there's going to be a pattern that you'll notice, so I'll just go ahead and tell you now, okay? Typically, like 90+% of the time, covalent compounds are formed between some nonmetal and another nonmetal, okay? On the last example, what were the two elements that made a covalent compound? Carbon and
Carbon and chlorine.
chlorine. Are those nonmetals?
Yes.
Yeah. Nonmetal, nonmetal usually is a covalent bond. Okay, they're all close to each other in the periodic table. Their electronegativities are similar, so they'll form a covalent compound. Okay, if you bond a nonmetal to a metalloid, probably also covalent. Okay, so again, another way to eyeball it, if you just see a nonmetal bonded with a nonmetal, probably covalent. You can double check with the electronegativity, but some teachers just skip to this and go, nonmetal, nonmetal is covalent. It's like, okay, it's true mostly, but I like to explain why. It's electronegativity.
Is everything that's not that just ionic? Like on a traditional sense, more like ionic?
Well, there's reasons for both, and then deductively you could say if it's not this, it's that. So it works both ways. Yeah. Okay. Okay, so fun fact about this is that one thing that's interesting about covalent compounds is you can get different ratios from the same elements. So for example, if I had nitrogen and oxygen reacting together to make a compound, you can actually get a bunch of different things. Okay? This is different from ionic compounds, which only react in certain ratios. You can get a variety of ratios for covalent compounds. Okay? So now we're going to get into, we need actually a different naming system for covalent ionic because of all the stuff that's happening. Yeah, we do this in physical science. Okay? So if I said something like nitrogen oxide, seems like a cool chemistry name, but then what are you talking about? These are 4 different compounds with different properties. I need a better naming system than something like nitrogen oxygen or nitrogen oxide.
Well, monoxide.
Yeah, mono. Yep. That's it. That's it. So we're going to do that. Okay? So that's for covalent. Ionic doesn't have that problem. They only react in one ratio, so they have a different naming system. Okay? So, but we'll get into that next week. Okay? So, ionic compounds typically are going to be between a metal and a nonmetal. Okay? So in the last examples we did, sodium and fluorine, metal, nonmetal, and then we had titanium and oxygen, metal, nonmetal. It's a pattern that shows up pretty commonly. There's some exceptions, but generally metal, nonmetal. You could also see it's across the periodic table, one side of the periodic table with the other side of the periodic table. Usually ionic. Okay, now I'm going to answer Adrian's question that you asked a little bit ago. Okay, electrons are transferred from the metal to the nonmetal. Okay, great, but how is that a bond? Well, let's think about charges. If the metal loses some electrons, they get ripped away. Do I have a neutral charge anymore if I lose electrons? No, what's my charge now?
Is it positive?
It's going to be some positive charge. So the metal becomes a cation. If the nonmetal has gained some electrons, what's its charge now? Negative. So now it's an anion. So now I have a positive and a negative nearby each other. They attract. That's where the bond comes in. So you transfer electrons, and now I have a cation and an anion near each other, and they stick together.
Will we make a compound?
Sure. Like in the lab?
Yeah.
Uh,
I'm just like curious how they make it. Like, cause you know,
It depends on the compounds that you're talking about. You've already kind of done that.
Would it be like heat? I'm assuming applied and like.
Some of them do it automatically. So for example, I mean, you put, remember we did the thing where you put it in the acid to see if it would react?
Oh yeah.
And the one that fizzed a lot, you did magnesium. And then you put it in acid, right? You did this reaction. So what happened here is you had magnesium react with the chlorine. And you made this compound, and then the gas was hydrogen gas.
So it's just.
So, I mean,
like,
so you've done it. You've done this in the lab. You just didn't know what was happening. So
So it's just like putting them next to each other and they automatically kind of do their thing.
depends. So sometimes you put them next to each other and it happens automatically. We also did this reaction. 3, 2 plus. Anyone know what I'm referring to? When we made iron?
Pumpkin.
So the pumpkin. We mixed those together. Did they do anything?
Yeah. They
On their own?
Solid iron.
They did. On their own though?
No, we lit it up.
You had to add energy to make it happen. Yeah. So there's a whole other side of chemistry where you talk about the energy involved. Some reactions are what we call spontaneous, where it will just happen automatically. Others are not spontaneous. You have to give them energy to start the reaction. So it just depends. Okay. But it's the same idea either way. Okay. So, but that's the idea when I'm forming an ionic compound, specifically from pure elements. So the reactions I just showed you weren't necessarily a pure element with a pure element. If I had that, then you have like electrons transfer and then they react. So different ways to do it. Cool? Okay. So we're talking about nomenclature. Did we talk about what nomenclature means? I kind of glazed over that.
No.
Okay. So this chapter is chemical nomenclature.
Naming.
Have you guys taken biology?
Yes.
Did you talk about binomial nomenclature?
Yes.
No. Biggest
What is binomial nomenclature about?
Isn't it about naming like the scientific?
Oh, yeah.
Naming animals. Binomial means to name naming system. Okay? Will already said it. Nomenclature means a naming system. So binomial nomenclature is a to name system we use for species, animals, plants, all that fun stuff. In chemistry, we're going to use chemical nomenclature. And fun fact, it is validated and enforced by the International System or Union of Pure and Applied Chemistry. Okay, basically the global organization that makes the rules.
What are
They
they?
can enforce rules.
Well, it's a group of scientists that get together and decide like we think this is best for everyone to do, just so we're all on the same page. Okay.
They also name like all the, like, or not
Yeah.
all, but
Yeah.
the bottom.
So we're using the IUPAC naming system. Okay, I'm not going to ask you that on a test. I'm just telling you this is like what official chemists use. Okay, the real stuff. Okay, and so here's the deal: covalent compounds and ionic compounds have their own naming systems. So we have to learn two separate naming systems. Okay, we're going to learn one of them today because it's super easy. Okay, so let's just move right on to covalent compounds. I can teach you this whole system in like 10 minutes. Okay, so we're just going to knock it out.
That's plenty of time.
Probably less than 10 minutes. Okay, so here's how what we're going to start with. Okay, if I give you a chemical formula, I want you to be able to name it.
By
Is it dinitrate
Oh, yeah,
something oxide?
You're close. Yes,
Nitrogen because you don't change the first one.
you're close. We're on the right track. Okay.
Di-
I'm telling you, this is covalent. Okay, if you wanted to double check, you would look up the electronegativities and make sure. Okay, but just believe me, it's covalent. Okay.
What was the 4?
Yeah, okay, so what we're going to do is we have to keep in mind that multiple ratios are possible. So we need a system for specifying how many atoms of each element there are. You guys are already on track. We're going to use prefixes. I think they're Greek prefixes. There are 10 of them that you need to know. If you have one of a certain element, or one atom of a certain element, we're going to use the prefix mono.
Did we do this in physical science?
You did, yes.
I remember this.
You did, yes. I think I taught it to you too back then.
Pretty sure I have a screenshot.
We were on COVID. I was standing right here, and I had a TV stand, and my laptop was right here, and I was just like, "Hi guys, welcome to COVID class."
They're like,
This is definitely the most exciting part of your day. Here we go.
Honestly, it kind of was.
Well,
It's better than
I'm glad.
class.
I'm glad. Were you that year? Were you freshman that year? What? Or were you the
Asking
year?
that question.
I just don't remember what year or what happened.
that's 2 years ago now.
Yeah, this one.
Got it.
It was our.
Were you both in 6th hour?
I was.
You were. What hour were you?
6 hours. I
Yeah.
guess again.
Got it. Yeah.
That
Sorry.
class-
And then 4th quarter we all came. All right, we're in
They
COVID
call
tales.
me Tyler.
Anyway, what do you think 2 is?
Die.
What about 3?
Dry.
4?
Pent. Wait, pent is fine.
Tetra.
Oh, yeah.
That's what.
Tetra. Quad is a good guess, but it's wrong. What about 5?
Pent.
Penta. 6?
Septa.
Hexa. Hexagon. 6 sides.
Do it.
7 is
It has the release
Hepta?
isn't it? It's I can't remember.
hepta.
Yeah, I had it.
Okay.
Oh, I can't remember these now.
There's different prefixes depending on what system you're in. There's like Latin and Greek and all that stuff. Okay. 8.
Octa.
Octa.
Yeah.
9.
Nueva.
Good guess.
Octa.
No.
Nana. 10.
Desi.
This isn't.
That's a 10th. A 10.
Deca.
Deca. Yeah. There you go. With a C.
Okay, I remember this now.
Not to be confused with deca with a K, which is a metric prefix.
It'd be even funnier if it was.
Deca with a Q. Okay, you need to memorize these. I will not give these to you on a test. Okay, you already know half of them probably anyway. Okay, you can memorize them. Okay, so let's name this compound. Okay, so here's the system. Do I need to go back?
No.
I don't know, like, the other half.
Okay, 5 seconds. Here, I'll talk through the next slide. Okay, so I'm going to give you some rules if you want to come back to it. Okay, rule number 1: we name the first element using the prefix. We don't change its name.
Okay.
So prefix for 2 is
Dinitrogen.
di. The element is nitrogen. So the first name, the first word in this name is dinitrogen. It is one word. Okay. The second, okay, and then there's an exception. You never use mono for the first element. You just say the element name. Okay. Have you heard of carbon monoxide?
Yes.
There's one of each, but carbon, you don't say monocarbon, you just say carbon, and then monoxide, one oxygen. So one carbon, one oxygen would be carbon monoxide. Okay. So this is dinitrogen. And then we do the same thing for the second element, except we use the IDE ending. Okay, so instead of oxygen, we're going to say oxide. We'll say tetroxide. Tetra for 4, and then oxide for oxygen.
Doesn't it get like shorter? Like, you don't write out like tetroxide, isn't just tetroxide?
Right, so with oxygen, it's kind of weird to say tetraoxide. We just shorten it to tetroxide.
But it's still spelled with an A, right?
Nope, you take it off. Okay, so oxygen is one where you technically take it off. So you would say penta, and like you don't say monooxide, you just say monoxide. It's just easier. Yes,
Do we just have to do the wacky ones with like?
yes, next week, or maybe tomorrow, actually.
No, you can make us memorize it again.
Oh, the polyatomic ions?
Yes.
Yeah, you have a bigger list this year too. Anyway, so first name, last name, okay? One word, just like you. First name, last name.
What if
Okay?
there's 3 or 4? Like 3, 4 elements.
We'll talk about that when we get there.
Okay.
For now, we're focusing on binary compounds with 2 elements. So, yeah. There's a different system for that, okay, depending on the compound. Okay? So we've got that, okay? Let's do some practice. Can you name these?
Yes.
Dinitrogen.
We just did the first one, dinitrogen tetroxide.
Nitrogen.
Nitrogen dioxide.
Nitrogen dioxide, again, good. No mono. If it's the first element, you just say the name.
Dinitrogen monoxide.
Yeah.
Dinitrogen.
Monoxide.
Monoxide. Okay.
Dinitrogen.
Good. So again, see, same two elements, but because of the different ratios, they're different chemicals, so naturally they need different names. Okay, so this system helps us with that. Okay, let's change up the elements. What's SI?
Silicon dioxide.
Silicon dioxide. Cool.
Sulfur.
This is not silicon.
Oh.
Sulfur.
Sulfur.
Hex. Fluoride.
Hexafluoride.
Alright.
Always the IDE ending. Notice the IDE ending for all these.
Wait.
Sulfur hexafluoride. Yes.
Somehow I heard the one that ended like grade, like potassium nitrate.
That is a thing. That's next week.
Oh, okay.
Yeah.
No!
Nitrate is a different thing. But it is a thing.
So many questions, but like the answer.
Well, kind of half answer.
At least now.
Yeah.
All of them are like next
Otherwise,
week
it's like
stuff.
spoiling it.
At least it's this week and not like next semester.
What if there's like 12? Like, it's only up to 10. So there's like more than that.
I will not give you one up to 12.
Okay.
I don't know what 12 would be. Is it dodeca? Dodecafluoride? I don't know.
Bring it up.
I'm not going to go past 10.
Yeah, they got some really wacky things after.
Cool? Okay, so then we also need to go the other way, which is actually easier, right? So if I gave you a name, could you tell me the chemical formula?
C and then
What is hydride referring to?
Tetrahydride?
Hydrogen.
Hydrogen, and then tetra means 4, so CH4.
Oh, yeah.
So if I were to give you steps, it's like one step. Use the prefixes to figure out how many
This is
atoms there are. Okay. Let's do some examples of that.
and H3.
Okay, so this is CH4. NH3, good.
H2O.
H2O. Oh, back up. No, back up. Ah. So yes, we call this water. The technical name is dihydrogen monoxide. That is water. Okay. This is nitrogen trihydride. It has a common name called ammonia. Okay, but that's that. Okay, I can later. Yes, there are sometimes memes where they're like dihydrogen monoxide, can kill you if you ingest too much, and people, if it's in your lungs, something about Obama like promoting dihydrogen monoxide in our food, and it's like just water.
hydrogen monoxide. Just the one.
This is also called methane. Okay, so it has a lot of these have common names, but the technical name is based on this. Okay, phosphorus pentachloride,
PCl5.
PCl5. How many fluorides are in hepta?
I have 7.
7.
Yeah, I have 7. There you go. Notice all of them are non-metal, right? So pretty common pattern for covalent compounds, non-metal bonded to a non-metal. Cool?
Yeah.
Okay, last thing. Okay. When we refer to particles of a covalent compound, we refer to them as molecules. This is different from ionic compounds. Those are not molecules, okay? And molecules are, I'm going to hold in front of the camera so we can see, okay, they are distinct particles, and they are not bonded to each other. So this is a model of a water molecule. If I had another water molecule, they would not be bonded. They would just be kind of floating around each other. With ionic compounds, all of the particles are bonded to each other, and you get a big crystal structure.
Oh, is that the weird?
It's like it makes minerals and rocks. Okay, but these are particles that are just next to each other.
Is that like the hexagon thing, like you see?
Yeah, so are we gonna draw like the hexagon things like they do?
I don't know if you're gonna draw them, but I can show them to you. So.
Yeah.
Wait, also, I don't think it's the like molecules are the like the lid.
Yes. So, well, molecule is one particle. So this is H2 and then O.
Oh, okay. So that's
And then I have a separate one that's an H2O, and they're not bonded together. I probably should have built. Do I have my ionic one over here? I always take it apart.
So the
That's a
two
bad example.
Separate elements are the molecules.
Right. So let me see if I can draw it. So like here, so I would have my H bonded to my O. That's a water, and then I have another water. Right. If I have a cup of water, I just have trillions of these just floating around each other. Okay. Now, if I had an ionic compound, which I'll show you later, okay, like sodium chloride, like salt, what you basically have is a sodium then a chloride, and then a sodium, and then a chloride, and then a sodium, and a chloride, just in a big grid. Chloride, sodium, chloride, sodium. Like that. So there's not really like distinct molecules. Like, is this a sodium chloride, or is this a sodium chloride?
It's all.
Or is that a sodium? Well, it all is. It's just a big grid that goes on until, you know, you run out. So this is called a crystal structure. So we do not refer to this as molecules because molecules are individual particles. Whereas with ionic, they're all bonded together. So anyway, just saying that for covalent for now.
So
Okay.
molecules will never be applicable to ionic bonds.
Right. Right, exactly. If you say the word molecule, you're implying a covalent bond. Yeah. Okay. And in nature, covalent compounds are solids, liquids, and gases. Okay. Air. There's covalent bonds like the nitrogens that are bonded together. Okay. Oxygen, all that fun stuff. Plastic, wood, water, milk. Okay. So lots of different phases. I say that because ionic compounds are pretty much always solids. They're rocks and crystals and minerals.
Are like fire and plasma, are those just energy, just classified as energy?
Fire is things burning and releasing light, so it's really not a compound.
Well, you said like solids, liquids, and gases. So like.
Oh, plasma is a phase that you get when you heat it up really, really hot. And I don't know where you would necessarily find that, like on Earth, unless you're microwaving some grapes, because apparently that is that, or on the sun. Yeah, I'm just picking the more common ones, I guess.
Like a shuttle.
Yes, potentially.
Or
I say that because ionic compounds are solids. They're crystals. Or salt. Cool?
yes.
Okay. That's all I got. Let's do a worksheet. It's an easy worksheet.
Is it a